Okay. Good afternoon, everybody. Welcome to our interdisciplinary seminar. It's a pleasure to have here today with us Dr. Hirani from the University of Illinois at Urbana-Champaign in the CS department. Dr. Hirani is an applied mathematician and computer scientist at the same time in the computer science department at Illinois. He works on problems that dealing with topology and geometry, and works on numerical methods related to any problem involving those tools. Before he went to Illinois, he was at NASA Jet Propulsion Lab in Pasadena, working on problems having to do with icy moons of Jupiter, but icy Earth on Earth. And he has also, of course, a broad background in graphics. In fact, for those of you who are old enough, you may remember Sun Microsystems. So now the Oracle, right?
Yep.
And he was also a researcher in image processing at Sony Corporation in Japan. He has a master's degree in computer science from Stanford and Caltech, and a PhD from Caltech in computer science with a minor in mathematics and control and dynamical system. And it's a pleasure to have him here. Thank you for coming. The floor is yours.
Thanks for the invitation and for your hospitality and for organizing, and to the math department for all the meetings. They were fun, back to back, but a lot of fun. So I'm going to talk about a small part of the work, some of my recent work. So it's not all of it. And so this talk is kind of an overview talk, and perhaps it's too broad an overview for, let's say, students of Hamid or the math faculty. So, I mean, I'd be happy to come back to the math department and give a chalk talk if you invite me. But most places where I go, it's I feel like how do you say, activist. I have to first explain why topology, and for most of you, I don't have to do that. But there are some who may not have worked on this. And you know, for activism, one of the most common phrases that every child knows is think global, act local, and that's very true in topology. The boundary matrices are these matrices which are built by very local relationships, but when you look at the boundary matrix, it contains all the topological information. At least all the homology groups are visible if you sort of operate on these matrices. So people in this area like Herbert Edelsbrunner, John Herer, Shayan Mukherjee, several other people have been making topology more robust with respect to noise by developing persistence. I'm sorry if I forgot somebody's name who's here and has been involved in that, but yeah, lots of people have been working on persistence, one of the hottest, most rising fields in sort of computational geometry topology. In fact, there's a conference called Sausage, Symposium on Computational Geometry, and this year it was in Chapel Hill, and there was discussion of making it SOGD, Symposium on Computational Geometry and Topology, but they haven't come up with a nice nickname like Sausage yet. So once that happens, more than half the papers I think were on topology. So clustering is a common technique in data analysis, and but it's the sort of the zeroth level topological information, how many connected components there are. So some people have been arguing that if everybody can do clustering well, there's nothing else to do. But people like Gunnar Carlson, he has written a sort of position paper in the bulletin 2 years ago on topology and data, where he gives examples where perhaps it's a single cluster, but it has a hole in it, or it's like a cyclical thing. So perhaps there is more information to be gathered from data than just knowing how many components there are. So graphs have started to show up in many examples in, for example, data analysis. But we feel, and many people feel, that graphs are just the beginning. When you throw in the 3 cliques and the 4 cliques and the 5 cliques and so on, you get a simplicial complex from a graph. And I'll show you my first example. Hopefully, I'll show you 3 sort of longish examples. The first example will be where you throw in the triangles, and then it's able to tell you more than what just the graph would have told you. And then a lot of analysis depends on a notion of distance, but this distance is kind of in a sociological context or in some sort of non-physical situation where you have data from some non-physical phenomena, and the distance may make sense locally, but perhaps doesn't mean much globally because the data might be very high dimensional but lying in some lower dimensional manifold. So one can't trust distance, and topology has this property of being able to ignore distances to some extent. And the coordinate system of your data may not really mean anything, and that's also sort of inherent property of topology that it doesn't care about coordinate systems. By the way, there's a very funny video, I don't know if anyone has seen it, by Colin Adams and somebody else. So this is called the presidential debate for the president of the United States of Mathematics. So it's sort of rigged to look like a presidential debate, and Colin Adams is representing the figure 8 knot, and his opponent, who's some famous mathematician, is representing the Euclid's algorithm for computing the greatest common divisor. And it's very funny. It's a 40-minute video, and they go back and forth, and this the other guy who's arguing against topology says, you don't want topologists to be a president if they with this sort of fuzzy, wuzzy, loosey-woogoozy geometry where they can do rubber sheets and do whatever. You want honest to God, good geometry, real geometry, and things like that. But it's very, very well done. I mean, I just fell off the, I can't reproduce it, but they did it very well. I fell off the chair laughing. So the methods that I use to solve these problems are generally matrix methods, many of which have come from trying to solve PDEs. And so most of the figures that I will show are things that are generated by software and algorithms that we built, and some of which is online. So these are, for example, the solution of a Poisson's equation for the scalar Poisson's equation on a square. This is sort of a two-form Poisson's equation, but you can also think of as Poisson's equation. This is Neumann boundary condition, this is Dirichlet boundary condition, and this mixed one. So this middle one is the vector Poisson's equation on an annulus and on a L-shaped domain. These are sort of two standard domains when people are trying to test their methods. And these are with what are called electric and magnetic boundary conditions. So these are 0 Laplacian, 1 Laplacian, 2 Laplacian. So I'll tell you about this later. But so many of the methods that we use were originally invented for solving PDEs numerically, including by us. But there are some methods that are invented in statistics, for example, which I don't use, but for example, some people claim that SVD came out of statistics, for example. And in topology, matrix methods have a long history. They are both, they've been around for a long time, and then there is new stuff happening. For example, there is this thing called computing the Smith normal form. You take the boundary matrix, and then you do some row and column operations, and then it becomes a block diagonal matrix from which you can read off the homology, you can read off the Betti numbers, you can read off if there is any torsion in this complex and whatnot. So this is, in fact, you will find it in any elementary algebraic topology book, like Munkres. Hatcher doesn't have that, but Munkres certainly does. And the new approach, I mean, new sort of use of matrix methods in topology and applied topology is the persistence, whole persistence sort of work that is happening. Some of the best implementations are done using matrices as the data structures, like the one by Dmitry Morozov, which is available from his website. So anyway, there's a hidden ingredient in the two things that or three things that I'll talk about depending on the time, which I haven't mentioned in the title. And that hidden ingredient is geometry, which, for example, here, I don't know if it's visible, but there is a red loop and a green loop which are in the same topological class. They're homologous to each other, meaning that they both are boundary of some patch on this thing. So here there's a red loop here and a green loop here. There's a red loop which is going around like this, then wandering around and then coming back, and then there's a green one. So these are all homologous loops, and topologically they are the same, but if you are interested in the tightest place on this statue, then you need to measure the distances and you need to use geometry. So for us, geometry will be that there's a notion of distance and then there's a notion of invariance, as in Felix Klein's program. So Euclidean geometry, you measure distances in the usual way, and it's invariant under rotations and translations, right? Anything which you can rotate and translate into another thing is congruent to or the same as. So modern geometry, the sort of stuff we use, differential geometry, calculus on manifolds, this is sort of inherently developed in a coordinate independent fashion, at least nowadays. In the old days, there were all these indices that you have to work with, but often the proofs are harder, conceptually they are harder. There's calculus, then there is vector calculus, and then when you generalize that to manifolds, you get what is called exterior calculus. It has appropriate notions of derivative, codifferential, Laplacian, and so on. So that's part of geometry, which is useful for some of the things. And people forget that things that are hot now in sort of data analysis, many of these things owe their origins to differential geometry and people working in geometry, like Cheeger constant, spectral graph theory, the idea of Laplacians of all kinds, Hodge theory, which I will show an example of in the next. So this is from the source of all wisdom nowadays, Wikipedia. Cheeger constant in Riemannian geometry. This what it is that it's a real number for a manifold defined in terms of the minimal area of a hypersurface surface that divides the manifold into two disjoint pieces of equal volume. So very natural thing to use in data analysis, and it is. And Jeff Cheeger proved an inequality but this is hard to compute. But you can compute the eigenvalue, and he developed an inequality that you can use to estimate or at least bound this constant. And notice that this is what at least Wikipedia says so, must be true, inspired an analogous theory for graphs. So we should not forget that mathematics is useful. I mean, some people would like to throw out mathematics. Some people say it's not necessary. Some people say it's not sufficient. So here's another example. A friend of mine who's at Ohio State, Misha Belkin, he's a machine learning, famous in machine learning, and he wrote this paper as part of his thesis in University of Chicago. And guess the department? Mathematics. Yeah. And his advisor was in computer science. If you do good interdisciplinary work, sometimes you can get cited very well. This is again, he developed the idea of a Laplacian without having a mesh around, so just using near neighbors on a graph and applied it to machine learning problems. Okay, so the first example that I'd like to show you is that of least squares ranking on graphs. So we have the problem is that you're given a graph of things that you want to rank. Initially, you are just given a bunch of things that you want to rank. These might be candidates, movies, sports teams, what have you. What you're given as data is pairwise comparison between some of them. So you don't have a complete graph. You don't compare everybody to everybody else, but some comparisons are given. So this is what's given to you. So from that data, we, for example, did this ranking of football teams, college football teams from 2009. So I don't know anything about football. I don't know, especially American football. I don't know how many players there are. Probably 2 teams play. That much I know. That's for sure. I don't know the rules. I don't know how long these games last. But I know that when the game is over, there is a number that says this team won over that team by so many points. And that's the only data I'm using to rank this. So we've used all that data from the whole year. If teams have played multiple games, then you can either add the score difference or subtract or sort of average the score difference. And all of those are variations that you can play with. Now, I mean, I didn't know that. I mean, I thought conferences were things that nerdy people like me went and talked about Hodge theory and stuff. But apparently, these are also called conferences. So this is ranking done by us. And apparently, this conference is supposed to be a good one. It has Florida and, I don't know, Alabama or some such. Yeah. Okay. So, and indeed, our ranking, not surprisingly, says that this conference generally looks good. So these numbers tell you roughly the ranking sort of color bar. So 1 to 19, slowly transitioning to blue, and then yellow, and then orange and red. Colors are not very visible. I know what you're wondering. Where is NCSU in that? It's that dot, number 66. And can someone tell me what is this outlier in this southeastern?
Ole Miss.
Which one?
University of Mississippi. Or wait, that might be Vanderbilt.
There you go.
Yeah.
It's Vanderbilt, number 71. So what a football expert thinks is also what we found, and Illinois is 81, worse
I'm
than
sorry,
you.
what are the edges?
The edges are, okay, sorry. So edges are the games that have been played. So conferences play a lot of games, and then there are interconference games as the season goes on. All right. So here's something that an undergrad did with us, developed this website using these tools to rank basketball teams using the data from 2010-2011 season. And this is, so our logo was, or slogan was, all the teams all the time, means we'll rank not just the top 25, but every 345 team. And I mean, okay, how will we test whether this is a good ranking or not? I'll show you in a second. But according to this, Ohio State was very good, Kansas was good, Duke was good, Illinois was not bad, but didn't do so well. But of course, what happens in playoffs is completely sort of different, right? It's a one game that decides your life. So you have, in the end of the season, the regular season, you have 32 winners of the conferences, and then 32 at-large teams, plus one team for play-ins. You have 65 teams. 2 teams play, 1 is picked. Now you have 64 teams, and then they play round after round and get eliminated. So what happens after that is not so dependent on ranking at that point, because it's that one game where you can easily be wrong. But by and large, experts would agree. I mean, and I don't know anything about basketball also. I mean, I know something about cricket, but nothing about basketball, nothing about football. And all I have used here is the score difference in the game, nothing fancy. I mean, there are people who do ranking. They go into, oh, the way the player runs and all kinds of detailed Markov chain analysis, blah, 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 everything, right? But I've done nothing. I've just taken the numbers, which is the score difference, and ranked the teams. And by and large, many people would agree. You might quibble about 1 or 2 positions, but I think we looked at, and probably 22 or so of them will show up in most of these lists that reporters, sports reporters make of what are the top 25 teams. And the main thing is that people just worry about the top 25, but on our web page you could go and look up which is the 345th team, which I don't remember. I wish it's somewhere in Illinois, but not Illinois. And so you can rank everything, right? You can, and then how do we know it's any good? But before that, NCSU was 104. So in that season, what happened was the final 4. So the ones that reached the semifinal were these, and Connecticut won, and they beat Kentucky by 1 point, Butler by 8. So just because Kentucky is ranked higher doesn't mean that you should put all your money into Kentucky, right? Anything can happen in these games, in playoffs. In a single individual game, who knows what can happen. Now, I have a colleague who, operations research kind of guy, who does bracket odds. So he has some technique of figuring out the probability that a particular bracket, so bracket is this thing where you fill in the teams starting from the initial 64 to all the way to the winner. And then, so people have, there's this thing called March Madness. People place bets and whatnot. So unfortunately, anyway, so this is what happened. Ohio State, which was top ranked, did enter the playoffs, but it lost after 2 games. So, so unfortunately, NSF doesn't allow field trips to Las Vegas. And I don't know, the odds are not available. So in Las Vegas, they maintain odds. But if you had equal odds for everything, which is obviously idiotic, right? It depends on how good the team is considered. But for example, you could go down in the rankings, and no bookie will know whether team number 250 is better than team number 275, right? But your ranking will tell you something. So here what we've done is that after the graph becomes connected, we start maintaining this data. You collect the number of games that you can predict correctly. You use the games that have been played till now. Use those to produce a ranking. And just simply use the ranking to predict who will win. The higher ranked team will win. That's it. Very simple. So I have games till day, let's say 150th. For the 151st day's games, I use the data from that up to that day. I do the ranking, and I say, okay, whoever is higher ranked will win. And then if the odds were equal, and I place, every day I place $1 on the higher ranked team throughout the season, I will, on average, be right 70% of the time, approximately. So this is using no information about the sports itself, just from this graph data. And on an individual day, you could be wrong. These are the playoffs, and either you are completely right or you're completely wrong in the end. But this is the cumulative, that if you keep counting how many you predicted correctly divided by the total number of games, is this red line, which is about 70%, certainly better than 50. Now, what can you do more from this? We'll go to that, but this idea is actually quite old, and it was written by a guy called Leakey in some obscure management journal in the 70s. But it showed up in Gilbert Strang's book. It's an example on chapter 2, page 106, on ranking football teams. And of course, he makes jokes about MIT and Harvard and whatnot. Just like there are jokes about the Caltech football team, undefeated since 1997, because they disbanded the team in 1997. So this idea is very old, the basic idea, but it goes beyond. So I'll tell you in a second. So the basic idea of this ranking is very simple. You got numbers on the edges. You're trying to come up with numbers on the vertices such that their difference matches the edges. But of course, you can't guarantee that always. So you try to match it in a least squares sense. That's all. That's why we call it the least squares ranking. So if you have a straight line, then there is no problem. You put 0 here, and to get a number 1 here, I should put 1 so that this difference is 1. So no error here, no error here. But once you get into loops, you can see that there are problems, right? But then you do it in a least squares sense.
So what's the meaning of the edge weight again?
The edge weight is how much, for example, if these were teams, so I prefer this one over that one, or this one over this one by these many points. That's what it means, edge weight. So it's a pairwise comparison. And if there are disconnected components, you do the ranking disconnectedly, and then you can't compare the different components because they haven't played each other, right? Fair enough. So let me give you a sort of simple example. So here's team A beat B by 1 point. B beat C by 1 point. And it so happens that, so when I put a minus, it means you can flip the arrow, and wherever the arrow is pointing is the winner. So A beat C by 2 points. So this data is what one would call consistent, because A should have beat C by 2 points, because this plus this is 2, and indeed. So if you go around the loop, 1 plus 1 minus 2 is 0. So whenever you have this phenomena that the total is 0, then you have a consistent data given to you. But sometimes that might not happen, right? So you might have A beat B by 1, B beat C by 1, but A beat C only by 1. So now it doesn't add up to 0. Nevertheless, A beat both C and B, so A should be ranked first, and B beat C, so B should be ranked second, and C should be ranked third. Here it's a loop. A beat B, B beat C, but C beat A. So what would the least squares ranking do in this case? It would give equal the result. You can work it out. Put 0 here, x1 here, and x2 here. Find the error. Just take the derivative, set it equal to 0. You'll get that all are equal. And which is right? So the least squares ranking tells you this much, that they don't prefer any over other. Moreover, sort of the idea was kind of developed further after the 70s by these 4 people, Zhang, Lecheng Lim, Yuan Yao, and Yin Yuye. So it's a mixture of Berkeley and Stanford crowd. I mean, when I saw this paper, I kicked myself. It's fantastic, really beautiful, general, great idea, really brilliant idea. And the tools were things that I already knew, I had been thinking about, but never thought about applying it to data analysis. I was just stuck in my PDEs, never thought about data analysis back then. Big mistake. But what they showed was how to use Hodge theory, which is a very simple idea that I will try to explain in a second. But this is from an old paper of ours, just to sort of illustrate. Hodge decomposition is a sort of old idea in engineering that any vector field on a square, let's say on a compact domain, compact closed domain, can be decomposed if there are no holes, simply connected. It can be decomposed into a curl free part and a divergence free part. So this is the vector field visualized using some technique. This is the curl free part, and that's the divergence free part. This is an idea that's quite useful in fluid mechanics, very, very useful in fluid mechanics. This is a book by my former advisor and his former colleague on fluid mechanics. And this is a picture from there talking about how you can decompose into the gradients and the divergence free part. So you can take the vector field on your fluid domain and decompose it into 2 pieces. And what use is that? Well, perhaps the most used numerical method in fluid mechanics is that you take a step or two, you get your new vector field, but it's supposed to be divergence free because the fluid is incompressible, but it won't be because of your numerical method. So let's take this vector field and make it divergence free by finding the vector field which is closest to this vector field in the L2 sense and is divergence free. So you do this Hodge decomposition to get, and then you again take a few steps, then do the projection again. So this method was invented in the 60s, and by Chorin, cited 2,300 times. Very, very well used method. So this is from his paper. He says decompose the vector field into divergence free and curl free. So we wrote a paper in computer graphics on uses for these things, and I'm going to just sort of just skip over. This is just sort of various needs that you have in graphics that you want to design a fluid flow. You take the vector field, decompose it into these two parts, and then you can enhance the vorticity part or enhance the other part, and then get a more complex looking vector field. Or you can take the vector field, decompose it, find the potentials, lower or raise the potentials, or erase some of the potentials, and simplify the vector field. So animators who design fluid-like things apparently use it. It's also, so I'll just skip over these. It's also used in solving boundary value problems in PDEs. It's fundamental, very, very important. I mean, for elliptic PDEs, it's ultimately what you do to solve an elliptic PDE is find the Hodge decomposition. It's used, it showed up in game theory. So my former colleague from Caltech, who's at MIT now, Pablo Perillo, has written a paper about how thinking of games as, I don't know anything about this stuff, I just heard him talk once, as vertices on a graph, and something about the gradient games are the ones that have, are the only ones that have Nash equilibria almost always, and so on. So there's something to be, and I don't know anything about it, so don't ask me. I'm just showing you that it's useful in many other things. So this is a sort of already modern classic by Doug Arnold, Rick Falk, and Ragnar Winther. It's a beautiful paper which describes how Hodge theory can be used in numerical analysis. Very, very sort of brings together ideas from function analysis, topology, geometry, numerical analysis, and gives you bounds on errors, stability results. Beautiful paper. So Hodge decomposition is actually quite simple if you do it in finite dimensions. You know how when you go through airports, they say 3, 1, 1. So I want you to remember only one thing, 3, 2, 1. If you have 3 vector spaces, 2 linear maps between them, then there is one decomposition. And it's an orthogonal decomposition. So basically all it uses is the idea of the 4 fundamental subspaces that Gilbert's triangle has popularized, that if you have a matrix, then the orthogonal complement of the image of A is the kernel of A transpose. The orthogonal complement of the kernel of A transpose is the image of A. So this idea used over and over again. So you have 2 things. All you need is that A followed by B should be 0. Therefore, the transpose is that B transpose followed by A transpose is 0. Then if you have such a situation where A followed by B is 0, then you have the decomposition of the middle guy into 3 pieces. There is the gradients, the curls, and the harmonics. This is what Hodge decomposition is, where this delta operator is, you start here, go A transpose A, go B, B transpose. That's the Laplacian. So this idea is exactly the gradient of, the curl of grad is 0, the divergence of curl is 0. So because that is true in vector calculus, this is why it shows up in vector calculus. But in general, in sort of exterior calculus, d square is 0, delta square is 0, and Laplacian is defined exactly like this. So this is why it shows up on manifolds. So there is a very simple, it's a very simple derivation that I will skip in the interest of time, but it's just linear algebra. So for finite dimensional vector spaces, if you have an inner product defined and you have that the composition of the 2 maps is 0, then the middle guy decomposes. That's all there is to it. So, so our sort of preliminary work, we haven't done very serious work in this ranking business, but what we've done is that different from what Jiang et al. Did was that they were thinking of using representing the data as a skew symmetric matrix, which is kind of wasteful. And since we had worked with PDEs, we knew that the right way to do it is to think of it as an oriented simplicial complex with numbers on the edges. So it's lots of savings of data and computation. And one thing we discovered during our experiments is that a solver that is a great favorite for certain PDEs and very popular and well developed in national labs actually works much worse than classic conjugate gradient solver because these problems are different from PDEs, and I'll show you in what way. And then you can use it, we've kind of used it as a sort of conjecture generator for random topology, which is a field which is quite hot in mathematics. It dates back to the work of Erdős and Renyi. There are these Erdős-Renyi graphs where there is a model for a random graph that every edge is there with a certain probability. Then people study what kind of topology can appear in such if you throw in the triangles, throw in the tetrahedra, and so on. And why do people do that? One, there is some relationship to statistical mechanics. The other is that it's a great way to generate examples. So for example, people don't know, so there are these spaces like dunce caps in topology, but they are very rare, and so if you want to find more examples, then you can show that with probability 1 something will appear. And we have done actual experiments with these data sets. So one thing I didn't mention is that so when you go beyond, when you take these, so what you do is you take these numbers that are on the edges, and finding those numbers on the vertices is the gradient part of the Hodge decomposition. But finding the curl on the triangles tells you how inconsistent that information is. And so it tells you how much you can trust that particular set of rankings. And the longer loops which are inconsistent are the harmonic parts, the ones which are not patched by the triangles. So how could you use this? Well, one idea would be to look for arbitrage opportunities. Suppose you have currency trading, which is actually very efficient, but maybe there is something where the information doesn't flow that rapidly. Say you could take dollars and buy rubles, take rubles to buy yen, take yen to buy yuan, take yuan to buy something else, and then somehow come back and make a profit because people haven't noticed that there is this long loop. So this inconsistency, the long inconsistency is the harmonic part which can help you detect arbitrage opportunities whenever you have some trading. So for example, if there is a barter economy where I give you 2 goats, you give me a bag of salt, and I take the bag of salt and get a Yugo car or something, then you could actually develop a meaning for what is the value of money in this sort of barter economy. So these are just sort of the numerical experiments that if you use this modern technique called algebraic multigrid versus conjugate gradient for computing the gradient part and the curl part, pretty soon you are seeing differences like 0.7 seconds versus 0.007 seconds, or 2 seconds versus 0.21 seconds. So this is supposed to be modern black box, great method for computer science, but apparently it doesn't work for the most basic graph problem where you're dealing with graph Laplacians. And I'm not an expert. So these are random graphs. These are Erdős-Renyi graphs with these many nodes and with these edge densities. And these are the computation times for using algebraic multigrid for computing the decomposition versus using conjugate gradient for computing the decomposition. And this is for the other kind of preferential attachment graphs for which there is not much theory in terms of random topology. So, I mean, I haven't looked at numerical linear with the eyes of numerical linear algebraists about what could be wrong, but you can see in these pictures that these graphs they have sparsity but no locality. There's no, the way you see in PDEs, right? In PDEs, it's a differential operator you're discretizing, so things are close by things are ones or minus ones, and the far away things are not. But in random graphs, things can be connected in all kinds of ways, whether it's Erdős-Renyi type or these preferential attachment type models. So here's a sort of to drive it home. If you take a mesh with these many vertices and these many edges, this is what the Laplacian matrix looks like. the scalar Laplacian. These are the non-zero entries visualized. Right? But if you take Edwards-Renyi graph with the same number of vertices and the same edge density, then this is what you get. So there is somehow a loss of structure. So I think this is a sort of a great opportunity for people who work in numerical linear algebra and want to have an impact in field of data analysis to start thinking about, and I know people in national labs are thinking about this kind of stuff, to how to approach problems on graphs. And this is just graphs, just the zero Laplacian. I mean, what happens when you do one Laplacian, two Laplacian on simplicial complexes which are random? I was telling you about this conjecture generator business. So these are experiments we did before we saw this paper by Matt Kale, who's done a great amount of work on random topology starting from his thesis onwards now. He's also at Ohio State in the math department. So this is a Edwards-Renyi graph with that many nodes, but with these edge densities. And this is the Betti number, the first Betti number. So initially there isn't any, and these lines are what Matt Kale proved in his analysis. But he didn't, at that point, when he first wrote his first paper, he didn't know that there was a special shape that this thing has. But then later on he wrote papers about that. So one could imagine that for Barabasi-Albert, nobody has done anything. So if you have a probabilist who works in random graph theory, you show him a few computations, they look at the graph, they have some ideas, they go ahead and prove and get all the credit, hopefully. So what next? The question that has been on everybody's mind who has a son younger than 9-year-old is which Pokemon is the best? And you know, this, for example, the fire Pokemon has 2 points over the problem is that it's not a symmetric matrix, so we have to ask for more funding, and it's not skew symmetric. It should be skew symmetric, but it's not. So next proposal will ask for how to develop ranking for Pokemon. Okay, so the second part is about these things called harmonic forms, which I'm going to probably have to rush through and come back and talk about in detail. So what are harmonic forms? These are generalizations of, so this is one part of the Hodge decomposition, the harmonic part. It contains the topological information. So things like torus have harmonic forms. The space of harmonic forms is two-dimensional because its homology has this loop, and so this loop and that loop. These are the two non-trivial loop classes. And if you have something with holes, then you have harmonic forms. The space of harmonic forms for 4 holes will be 4-dimensional. And you can imagine uses for such things. They've been used in computer graphics and are very useful in PDE solving. I'll tell you in a minute. But so harmonic forms are a generalization of harmonic functions. Harmonic functions capture the notion of connectedness, right? If you have 2 components, then you'll have 2 independent constants, which are the space of harmonic forms. So the space of harmonic functions, will be 2-dimensional. Harmonic vector fields or harmonic 1 forms have to do with how many holes you have. So there will be 2-dimensional for this and 4-dimensional for that. And then there are higher order versions, higher dimensional versions. So this is a solid ball with a hole in it where the harmonic 2 form is visualized as a vector field. And there should be only one, and there is one. So they are used in, they are sort of the step 1 or step 0 in solving a PDE. If you're solving Poisson's equation, then ultimately what you're doing is, it's not even well posed. Now, is there something to write with? I mean, I see a nice board here, but if there's some chalk.
Yeah, actually, for the distance band students, it would be better if you use a smart board. I'm not sure if Dr. Krim can.
Oh, that's fine. I'll just talk through this. So if you solve Poisson's equation, Laplace u equal to f, then unless you remove the harmonics from f, the problem is not well posed. Moreover, when you solve it, your method has to solve orthogonally to the harmonics. So here's an example from Doug Arnold's paper, Arnold Falk-Winther paper, that if you do not take care, So this one has one-dimensional harmonic space. If you do not take care to solve orthogonally to the harmonics, you get some solution to the Poisson's equation, and it seems reasonable, doesn't blow up, goes nicely around, but it's wrong. The correct solution is this one, and you get it only if you know what the harmonic vector field is, and you solve orthogonally to the harmonic vector fields. It's, as I mentioned, used in computer graphics for designing vector fields. So if you have a complicated domain, you underlay a nice smooth vector field which is harmonic. So yeah, that's okay. So you underlie, so you lay down a harmonic vector field and you throw in some gradients and vortices, and you get a vector field. So it's used in there also. I'm going to skip over de Rham complexes and come back and talk about it some other day. So this is sort of a thing called finite element exterior calculus or discrete exterior calculus, which I've been working on since my thesis days. But there is a way for which we won't have time to eventually find a matrix which represents the Laplacian. So the entries in this matrix are these things called discrete Hodge stars or mass matrices in finite elements, and these are the boundary matrices. This is the boundary matrix, this is its transpose. So once you have this matrix which represents the Laplacian of any dimension, you can then find its basically kernel, you can find a basis for its kernel. And one way to do that, to find harmonic forms, one way to do that is to find the eigenvectors corresponding to the zero eigenvalue. So certainly one can do that, and people in PDEs do that. But you have no control over what kind of a harmonic form you will get. You will get a two-dimensional kernel, but it will do whatever it will do, no control. So for example, here are these four holes. The harmonic forms that we got by finding the eigenvectors goes partly around this hole, partly around this hole, partly around this hole. But if you are a vector field designer, you might be wanting to focus on swirling around just one hole, for example. And that control is something you won't have with this. Unlike the sort of method that I'm about to tell, the least square space method. So here's a comparison of the two. This is using the least square space method that I haven't really written down, and then this is using the eigenvectors of the Laplacian. So how do you get that control? So you get the control by, so topology comes to help here. You know that the harmonic form has very much to do with, there's a famous theorem that in every cohomology class, the smallest form in the L2 norm sense is the harmonic form. So this is the reason why the space of harmonic forms is isomorphic to the cohomology group, which is a vector space. We're talking about real cohomology. So what you do is you find a cocycle. In this case, you can think of it as a picket fence. In any triangle, you'll have two edges selected. These are easy to find in linear time for surfaces. So you find a picket fence joining a hole to the end, and this is a cocycle. Its boundary transpose is 0. And then you try to find the smallest guy in its cohomology class, and that will be your harmonic. That's all there is to the method. This is just comparison with, yeah. So you're given a class, a cohomology class, real cohomology, and you're trying to find the gradient part such that you minimize. So by doing omega plus d alpha, you are staying in the cohomology class of omega. Omega is given to you. It's a representative, right? Like that red picket fence. And then by using omega plus d alphas and searching over all alphas, you are staying in the cohomology class of omega. And just minimize that. And how do you do? And when you write it out using finite element exterior calculus, just pops out this. If you've done any numerical linear algebra course, you should immediately recognize this as, anyone know the name of this sort of an equation? Think A transpose and identity for that. A transpose AX equal to, forget the minus, A transpose B. Anyone recognize that? These are the normal equations that you use to solve least squares problems. So these are weighted normal equations. So it's basically just a least squares problem, not surprisingly. And then we proved that when you solve this problem, what you actually solve is the lowest order finite element equations. Exactly. The code is very simple. This is using our PyDeck software. This is in Python. So just this much code. This is just import stuff, and then computing the harmonic is equal to omega plus d alpha. Just almost like what the math read is what the code reads like. So, and these were the picket fences that we used for the torus. And you can do other things. You can find linear combinations of the harmonic forms by drawing picket fences, joining the holes, and have fun doing whatever you want. But if you zoom in, you will see that they only go around the hole you picked, and they only flow past all the others. So they are very precise and very they're very robust to perturbation. So here's a cocycle. Here's another cocycle in the same cohomology class. It connects this hole to the boundary. Here's another one, even goes past that boundary. But up to machine epsilon, these three vector fields are identical. So solving the least squares problem, because topology says it must be, and it is. So this is sort of interplay between topology and numerical analysis that is happening nowadays, which is very interesting. And this is a harmonic 2 form for a ball with a cavity, solid ball with a cavity, nothing fancy. This is just comparing, trying to show off. Okay, forget it. Okay, so you can use this kind of harmonic form computation. Harish, who's Hamid's student, is been working on one approach which is distributed to localize holes. So this is a very sort of simple 4-line code that one can write based on the way Winde Silva and Rob Dreist model sort of abstractions of sensor networks as vertices on the plane, let's say, with a sensing radius, and you draw an edge if 2 things can see each other, and you fill in a triangle if 3 things can see each other mutually. So you might use this in things like, okay, let's skip that one. So localization has its uses, and here's localization computation using harmonic forms, but this is not distributed, which is actually very a great thing if one can do, which Harish and Hamid have done, is to do this computation that I'm about to show in a distributed way and in a more crisp way. This is a very sort of crude localization. So you have a bunch of points which are the sensors. They have been connected by these edges. You fill in all the triangles, and now you want to detect if there is a hole in it, and the hole will be coming from the kernel of the Laplacian, the one Laplacian, and you compute the harmonic 1 form and you plot it on the edges. So you take a random set of values on the edges and do a Hodge decomposition. The stuff that's in the harmonic part is this thing that I've shown. So I've drawn thicker edges where the component is larger, thinner edges where it is smaller, and you can at least visually see this sort of localization. But as I said, what Hamid and Harish have been doing is much more beautiful, using dividing up the domain into pieces and using distributed algorithms, being careful about the complexities and so on. So, but there is another approach to localization and related problems that I'm going to talk about, which are very close and closely related to these problems that we just discussed. So what we just discussed was finding things which are cohomologous to a given thing with the smallest norm, or which are now we are going to talk about something which is homologous to a given thing with the smallest norm. The only difference is that the norm will be, instead of the L2 norm, we'll use the 1 norm. So the example that I showed earlier, so you're given this red cycle and you want to find the homologous cycle which is the smallest in number or length, you pick. So the smallest cycle homologous to the given one. And so these are 2 examples done using the technique that I'm about to describe. This is an interesting example. Goes around the neck and under the arm. breaks up into 2 cycles. So this red thing is homologous to that, and you can tell because the blue patch boundary is this, this, and that. This is a 3D example, very silly one, but nevertheless doable, just to show this, because before we did our work, there were no algorithms for higher than 2 dimensions, and I'll tell you what the problems with even the dimensions for localizing 1 cycles was. But this is the input cycle. So this is a ball with a hole, solid ball with a hole, which has been cut to expose the insides. The initial cycle is this one, and the one homologous to it is, of course, the inner sphere. Nothing fancy, but just as a sort of a proof of concept. Same thing on a torus. So this is useful because ion channels in membranes have holes, and people actually do find the smallest place because that decides how big a molecule can go through. So there's actually a server called hole, or a program called hole, that people use in biophysics. I've talked to people who actually use this stuff. But it makes the assumption that your channel is straight, they align a z-axis with it, they put spheres, till they grow spheres till they can't grow anymore, and then they use this set of spheres to find where is the narrowest part. So that's the technique that is used. But if the hole was curved, or if you had some sort of part of tissue where you have, let's say, lots of vessels, and you want to somehow characterize the smallest parts of the vessels to quantify this tissue domain, then you wouldn't be able to use something like hole. So this problem, what is given is a simplicial complex and a chain. So I mean, for now, think of chain as just a bunch of numbers on, let's say, one chain will be a bunch of numbers on edges, such that if I switch the orientation, the numbers become negative. So if you have 100 edges, you will have 1, 1, 1, 3, 7, 9, 4, 9. And if I switch one of the edges, that entry will become negative. Just for now, that's enough to think about it that way. And what we'd like is something which is homologous to the given one and is the smallest. And smallest can be the number, or the area if it's a 2 cycle or 2 chain, or the length if it's a 1 chain, or volume, and so on. So we call it the optimal homologous chain problem, OHCP. And you can write it as this. You want to minimize the one norm, a weighted one norm, where the weights are the lengths of the edges or the areas of the triangles. So minimize the weighted one norm subject to this homologousness constraint. Given C, their difference should be the boundary of something. This is that blue thing we saw, the blue patch. This is the red thing, the long red cycles, and this is the green cycles. And the constraint is that these are integer vectors. So before us, people were using, instead of integers, they were using mod 2 homology. So in computer science literature, what you could find was treatment of this problem for surfaces using mod 2 homology, meaning that if I want to draw a loop on the surface, I say this edge is 1, this edge is 1, this edge is 1, this edge is 1, and I put zeros on all the others. And when 2 ones meet, they become 0. So if 2 triangles meet and they share an edge, and there's 1 on each of them, it becomes. That's how you kind of push off from one curve to the other one by cancelling using the triangles, right? I'm just giving you an intuitive picture. So that's Z2 homology, and what Chao Chen and Friedman, his advisor, showed. It was shown in maybe 2008 or 9, but finally published in Soda in 2010. They showed that in Z2, this problem is NP hard even to approximate to within any constant factor. So if you want to even find an approximately optimal thing, you can't do it. So they actually proved it, and they proved it by reducing the closest vector problem, closest code word problem, where you're given a dictionary of code words, and you're given a word you want to match or make up as a linear combination of these, and you use Z2 linear combinations of the dictionary to make up your code word in a way that minimizes the distance, Hamming distance between the given word and the one that you made up. So coding theory thing. So that is known to be, and therefore they reduced it and showed. So they constructed this nice topological problem from the given dictionary and made this into a topology problem. So if you could solve this problem, you could solve that problem, but that one is known to be hard. So our main result was this surprising thing that if you, I mean, people thought that Z2 is simpler because you have just zeros and ones, and we said no. If you have 0, 1s and minus 1s, and you allow orientation to decide whether something is 1 or minus 1, then you naturally will get integer homology, and if you do, then you can actually solve it in polynomial time, so which is okay. Maybe it's not linear time, but much better than NP hard in my opinion. And this is for relatively. So we showed that we can solve it for these things which we call relatively torsion-free spaces. Is there a question from offsite? Okay. So specifically, our theorem was that suppose you are given a simplicial complex, and let's say it's dimension n plus 1. Then, if you are interested in, what we proved was that the top dimensional boundary matrix will be totally unimodular if and only if you have this condition. So it was an if and only if condition that we found, that the relative homology the n-dimensional relative, the codimension 1 relative homology is torsion free, and this is to be true for all subcomplexes L0 and L. So it's kind of technical sounding, but it has many interesting implications, and it was a lot of fun to prove. So the proof is very fun. It's once you see it, it's okay. Maybe takes 15 minutes to go through, but it's quite easily something that a grad student could have done if they knew what they were trying to prove. But finding what you want to prove was, of course, always the hard part. So in particular, what this allows is, so this does a characterization of which boundary matrices are totally unimodular. And why is this useful? Because since the old days in linear programming, it has been known in the 1950s that linear programs look like minimize some linear constraint subject to some, minimize some linear objective function subject to some constraint ax less than or equal to b. If a is totally unimodular and b is integer, then the result is always integer. And the reason that is true is because the constraint polyhedron in that case has only integral vertices. So since the linear program always finds a solution on the boundary of the polytope, the solution is automatically integer. So we actually, you can see this in our code, you get exactly ones and minus ones. We use real arithmetic, don't ask it to do anything special, but you get precisely ones and minus ones. So this characterizes the only way you can have a boundary matrix which is totally unimodular is having this property. We completely characterized it. And torsion is sort of algebraically difficult sounding, but homology groups can be written usually as some copies of Z plus some copies of Z mod, let's say Z mod A plus Z mod B plus Z mod C, where A divides B, B divides C. So whenever you have these trailing things, then you have torsion, and it usually happens when you take, let's say, a disk, you take a circle and you take a disk, and if you wrap this disk, if you glue this disk to the circle, the boundary of this disk to the circle, and you wrap it around 2, then you'll get torsion coefficient of 2. If you take this disk and glue the boundary to the circle by wrapping 3 times, you'll get a torsion coefficient of 3, and so on. So we use this to solve an interesting problem in computational knot theory. So this problem of finding, so the famous problem is, given a knot, is it a trivial knot? So great problem, still open. So given a knot, is it a trivial knot? How can you solve it in polynomial time? So it's known to be decidable, but so knot is just a curve, closed curve in, let's say, R3 in this case, and we want to find, but instead of that, we are solving a simpler problem. This is also a famous problem. The problem is find a spanning surface of the least area whose boundary is the given knot. Not the minimum genus surface, but find the surface with the least area. So here, that's the surface I'm visualizing. So this was decided, this was shown by Haken, this least spanning area problem. It was shown to be decidable by Haken, and then it was in John Sullivan's thesis. Haken was at U of I, Sullivan was at U of I, I'm at U of I, and my collaborator Nathan Dunfield is at U of I. So good things happen there sometimes. It's useful. Let's not care about that. So more generally, if you're given a 3-manifold containing the knot, and you're given this manifold as a simplicial complex with areas assigned for each triangle, and the knot is given as a bunch of edges, sort of a loop made up of edges, and you're only allowed to use the triangles that are given to you. Can you find me, patch up this knot, find me the least area surface? So this is the input, the complex and the given knot, and you want to find the smallest. So we call it the OBCP, the optimal bounding chain problem. So Ian Agel, Joel Huss, and Bill Thurston, who passed away recently, maybe 2 weeks ago, a great geometer and topologist, they showed that if the manifold, embedding manifold, is a general manifold, then this problem is NP hard. But we showed that if you are in, let's say, R3 or S3, so if you have trivial second homology, then and you have an orientable manifold, then you can solve this in polynomial time. This was a very easy application of, well, part of it was easy, part of it was some desingularization argument that Nathan is good at, but so I'll skip the sort of simple part of the proof and not at all show you the hard part, but instead I'll just show you. So here's the Hamiltonian cycle of the cube vertices. You visit all the vertex once, right? So this is you visiting all the vertex and returning back. You embed this in a tetrahedral complex, and now find me the surface whose boundary is this red thing, and this has a name. It's called the shirk surface. So this is a combinatorial shirk surface. Looks like a bed, uncomfortable saddle, I don't know. So here's the knot, embed this in a tetrahedral mesh, find me the, using the triangles that are given to you, the smallest. And NP hard in general, polynomial time in the conditions that we have. So you can think of it as a sort of preprocessor for minimal surface finders, because unless you are careful, you can get the wrong topology. So this is a wire that goes around, goes up, and comes back down, just twisting once completely, 2 pi rotation here. If these loops on the top and bottom are far away, then it's cheaper to patch this and this thin strip. If you squish it closer, it's cheaper to patch the sides. And in fact, that's what will happen. The thing on the right is a torus with a hole, not easy to see, but it's a torus with a hole, and this is just a disk. So the topology will be different, and if you set it off, your minimal surface finder, which uses PDEs and sort of whatever mean curvature, flow and whatnot, will get singularities and will get stuck. So you first need to fix the topology, then give it to your PDE solver. So another way in which sort of numerics and topology interact. And we had lots of other fun with it. Like you can, given this side of the triangle, rectangle, and that side, find me the shortest path without specifying. And this is easy to do using Dijkstra. Take every pair, and you can do something fancier, right? Take every pair on the boundary and use Dijkstra's to find the shortest path, or do something fancier than that. But can you do it in higher dimension? And the answer is no. There is nothing there in higher dimensions. Okay, so I'm going to close quickly with what I've talked about. Everything that I've talked about, the geometry or the combinatorics, counting or measuring, is in the cost function, and the topology has been a constraint, that find me something in this cohomology class or this homology class. So if you put them side by side, you can see how similar they are. This is the least squares problem for finding harmonic forms. This is the one norm minimization problem for solving the optimal homologous chain problem, and the OBCP related to that. So just by changing the norm from 2 to 1, changing vectors from real to integers, and changing the boundary to boundary transpose, these two very different things become kind of related. This is solved using linear programming. This is solved using linear algebra. So we have a library, software library called PyDeck for both these experimenting with various kinds of complexes, RIPS complexes and cubical complexes and general simplicial complexes, embedded, non-embedded, abstract simplicial complexes, manifold meshes, and you can do PDEs or experiments in topology or graphs or simplicial complexes using that. Okay, so lots of stuff one can do. I think I'm out of time at 2 o'clock. Okay, so I'll just skip that. People have been looking at higher Laplacians in theory as well as in other places. I just wanted to show this spectrum of a resonant cavity. A resonant cavity is something that is an electromagnetic cavity whose spectrum you can measure, and this is the setup in Feynman's book. This is from Feynman's book. And I have a physics student who's having some fun measuring the spectrum of a can. And we are doing many other things which I don't have time to talk about. So I'll end here. These are my students, and this is joint work with Alan Demlo, Tamal Day, Nathan Dunfield, and Bala Krishnamurthy. My students, Kaushik is in computer science, Mark is in physics, Han is in math, and Seth is in mechanical engineering. And one of my grants is from math, the other is from computer science. Okay, I think I'll end here. Thank you for your time.
All right. We have some time for questions. Any questions?
Yeah, I can ask one quick question. So, I don't exactly work on topological problems, but my interest was more on the graph theory part that you mentioned. So, for the ranking problem that you started to talk with, the approach that you took was completely, you just showed the graphs, for example, but you didn't quite mention the matrix component of those graphs, right? Like graph theory and matrix theory go hand in hand, right?
So they're all in the papers.
Okay.
It's a least squares problem involving the boundary matrix.
Right. So my question was that when you are solving the least squares problem, for example, can't you pose the problem as the matrix rank minimization problem?
Matrix rank minimization problem?
Yeah.
Why would that be connected?
Well, first of all,
So you take the skew symmetric matrix that represents the one cochain, and then
well, I'm not even going into those kind of details. I'm just thinking that, say for example, every graph can be represented by a graph Laplacian matrix, right? Like say for example, then if I'm trying to do graph design, I don't exactly know the application that you're coming from, but generally in graph theory, what we sometimes do is that we want to design a graph, a weighted graph, for example, and try to define its topology, for example, by posing the graph design problem as a convex optimization problem which minimizes the rank of the Laplacian. So maybe it's a different context or something, but it somehow looked like when you're drawing that triangular graph, it's a digraph for it. In your case, it's even more complicated because it's a directed graph.
well, it's an oriented graph, so there's no notion that you can only travel in this direction. It's just an oriented simplicial complex, so it's a slightly different concept. There's no, the fact that it's oriented that way is arbitrary. I could orient it that way and just change the number to the minus of that. So it's there are no self loops. So you take a simple graph and you just think of it as, put down the orientations on the edges and think of it as an oriented simplicial one complex. Yeah, but I don't know what this application is, but if you can sort of mention where I can look at.
So the matrix rank minimization problem is the work by Stephen Boyd in Stanford, right? And they do
Yeah,
a
but
lot
this
of
application using for Laplacians for graph design,
right.
is it also in his papers?
Well, you can find it, in many. So for example, I work in power systems, right? So for example, if you're doing a power system planning problem, which means that you are trying to plan how you are going to design your grid, and the nodes in these cases are like generators, for example, and the edges are the transmission lines. So you're trying to design which generator should be connected to each other generator, and what kind of reactance should you have for the transmission lines and stuff. So that's like a graph design problem. And you can pose those design problems as the rank minimization problem of the Laplacian matrix that defines that graph.
Right. But those are probably much harder. So this is sort of least squares is the simplest optimization that you can think of, right? This is
So it wasn't quite giving you the exact number that you wanted, right? So that's why I was wondering that, can the accuracy be increased by posing it as a rank minimization problem? Because
What order Laplacian are you talking about?
I think he's talking about graph Laplacian.
I'm talking about graph Laplacian
Oh, graph
matrices.
Laplacian.
Yeah.
But the thing is that, so this is sort of provably the closest in the L2 norm, right? So given a one cochain on the graph, if you throw in the triangles and think of it as a simplicial two complex, then this decomposition is provably the gradient part is the closest in the L2 sense to the given data. So it's a slightly different problem than what you're thinking. The graph is given to you, yeah.
Yeah, I was trying to design the graph, but over here, I think your graph is already fixed.
Yeah, graph is fixed. It's a very simple optimization problem.
Any other questions?
Well, it's just a sort of a technical thing right in the middle somewhere. So when you were talking about the Erdős-Renyi graphs and showed this nice graph chart and Matt Kale's work and so on, what kind of coefficients is that using?
What do you mean coefficients?
Oh.
Real coefficients.
Oh, okay.
Yeah. It's real cohomology.
I see. So it's over a field, so you don't see any torsion.
You don't see any torsion.
Okay.
So actually, I did do a little bit of computation for some other people who work in random graph theory, but we haven't gone very far in that. But I met Roy Meshulam at Darkstool earlier this year, and we did a little computation for him.
Okay.
The other thing that do you have anything working like in the round cohomology and things?
Yeah, it's all this.
You-
Other half of my life.
You
when we saw
actually have
yeah, it's
you-
all there. Yeah.
You have software and everything.
Yeah. Biotech has everything. The lowest order. So it has. You can do discrete exterior calculus, or you can do Whitney one forms, which is sort of morally the linear, piecewise linear. And then we haven't gone beyond for higher degree polynomials, but you can solve a PDE on a mesh using the code that we have. I do only elliptic PDEs so far.
I don't do PDEs.
Okay. But elliptic are the easiest.
Any other questions? All right. If there are no more questions, let's thank our speaker again.